So the title of my presentation is Numerical Simulation of Ductile Rupture at Low Triaxialities using an extended Gurson type model including void shape effects. First, the authors, myself and my previous PhD student who are with the Université Pierre et Marie Curie, France. There is also Dirk Bohr, who performed some experiments, who was at the time with the Laboratoire de Mécanique des Solides, École Polytechnique, who is now in the École Polytechnique Fédérale de Lausanne, and Viggo Kjærgaard, who I think he needs a little introduction. He is with the Department of Mechanical Engineering in the Technical University of Denmark, and he performed some numerical micromechanical simulations. So this talk is about will be about ductile rupture at low triaxialities when void growth is not so important, but void shape changes are important. So this is the outline of the talk. After an introduction, I will introduce a model which is labeled ML here. It is an extension of Gurson's model which includes void shape effects. Then I will quickly comment on the numerical implementation of this model in finite element codes. Then the core of the work is the qualification, the assessment of the model by comparison with the two things. First, some micromechanical simulations, numerical finite element simulations of Kjærgaard, of void which is subject to both tension and shear. And there are also some experiments. There are some comparisons with some experiments which have been performed by Dunant and Moore on butterfly specimens. So the first introduction. What models are available for plastic porous materials for ductile rupture? Well, the most classical ones are probably there. There's the famous Gurson model, which was designed for spherical voids. So the voids are spherical and assumed to remain spherical, so there is no effect of void shape. And this essentially applies to high triaxiality situations when void growth dominates. Then, more than 20 years ago, essentially with a very bright PhD student of mine named Gurson, we performed the first extension of this model by considering spherical voids, which are ellipsoidal voids with the axisymmetric ellipsoidal voids. So you have two distinct axes, and there's one shape parameter, which is the ratio of the two axes. And even more recently, with another PhD student, we at last managed to extend this model to general ellipsoids. So then you have three different axes, and you have two shape parameters. And again, void shape effects are expected to be important at low triaxialities, because in the case of high triaxialities, void growth dominates. So what are the aims of this work? It is first to propose supposedly optimal finite element implementation of this model, and second to assess the capabilities of this model by comparing its predictions to the results, first of some finite element micromechanical simulations of Kjærgaard and co-workers, and also to some experiments. And all of these micromechanical simulations and experiments were performed under various conditions, but were mainly interested in conditions of low triaxiality when void shape effects are important. First, very short presentation of the model. There is an extended Gurson-like criterion. So this looks like, this looks like Gurson's criterion. You have a quadratic form of the components of the overall stress tensor here, which takes the place of sigma equivalent. Here you have a linear form of the diagonal components of sigma. You have the famous hyperbolic sign. You have the porosity, the usual porosity F. You have here sigma bar, which is the average yield stress of the matrix. But the main thing which makes this criterion distinct from that of Gurson is the appearance of G here. And G represents, well, it has a rather complex definition. I call it the second porosity. It is zero in the case of prolate voids. It is spherical voids. It is non-zero for oblate ones. And for penny-shaped cracks are oblate voids which are completely flat. Then it is what G reduces to what is commonly called the crack density. And it is obvious intuitively that such a parameter should enter the criterion, because if you have cracks, the porosity, since the cracks are completely flat, the porosity is zero. So if you just take Gurson's criterion, if the porosity is zero, the criterion says that there is no effect of the cracks, which obviously is wrong. So So that is why G must come into play somewhere. So the other elements of the model are, there's a plastic flow rule which obeys the normality law. This is not an assumption. It may be shown that when you perform homogenization, if the normality law is obeyed at the local scale, then it is obeyed at the global scale. And there are also evolution equations which I will not detail for the internal parameters, the porosity, the magnitude of the axis of the voids, and their orientation, and also, of course, the overall yield stress. I will go quickly over this numerical implementation. There is a nice framework which was put forward, which was defined by Alpha and Nguyen, which are essentially known in France. Generalized standard materials. Such materials obey a kind of extended normality rule, not only with respect to the plastic strain, but also internal parameters. And these models obey some nice mathematical properties which have important consequences upon the numerical implementation of the material. So it can be shown that this model fits, just like Gurson's model, it fits into this class. But you have, in order to fit the model into the class, you have to assume that the porosity and the shape and orientation of the voids are fixed. So this seems completely stupid and unrealistic, but it's not so stupid because it's possible to design a finite implementation. It's possible to design it so as to benefit from the nice mathematical properties of a generalized standard material. And the main property is that you have existence and uniqueness of the solution of the local problem of plastic correction of the elastic predictor. You don't have existence and uniqueness of the overall boundary value problem, but at least for the projection problem, you have existence and uniqueness of the solution. The key point here is to adopt an explicit algorithm with respect to these parameters, because then, well, the porosity, the shape, and orientation of the voids, because when you do that, when you calculate from T plus delta T, the porosity, and the shape and the orientation of the voids are fixed. So it is as if they were fixed in the model, from a practical point of view. We have implemented this model into two finite element codes, the Sistus code developed by ESI, and also the Abacus program, well-known program, through a user material subroutine in the second case, and I've made this UMAT freely available at this address, so if you want to use it, you're completely free to do it. I now come to the assessment of the model. First, I will talk about the finite element micromechanical simulations of Treguard and coworkers. So you have schematic of, it's not all the simulations, but just one case. So you see you have a unit cell which is embedded into a periodic medium, so you have a periodic distribution of voids. And Vigo subjects this cell to tension in this direction and shear in this direction. So you see that the initially spherical void becomes roughly ellipsoidal, it rotates, the shape changes, and the rotation also changes. So the micromechanical simulations are performed by the finite element method. They consider meshed cells. I didn't show the mesh in the previous figure, but they are completely meshed. They contain an initially spherical void. They are subjected to combined tension and shear. And the local criterion and flow rule are those of von Mises and Prandtl-Ross. So there is no hypothesis about some homogenized model in these simulations. They are rigorous. And we compare the result of these simulations with some model predictions which have also been obtained by a finite element method. Here we have considered a single element, that's very simple, obeying the homogenized ML model. I have to introduce two parameters. Kappa is the ratio of the tensile stress over the shear stress, and then C is a kind of loading angle which increases as the loading proceeds. So there are various quantities here. First you have the shear stress divided by the initial yield stress as a function of C, which is the load angle, and there you have different values of kappa. So this is kappa is 1.5. This is an essentially tensile load, and here on the contrary you have an essentially shearing load. So you see that the simulations are well reproduced by the model, including the final decrease at the end. I'll come back to that. The evolution of the porosity is also quite well reproduced. You see that in the cases where the shear is dominant, you don't have any significant void growth. In spite of that, you have a final decrease of the stress. This is for the orientation of the voice. Well, this is not perfect, but it's not too bad. And this is the evolution of the three axes here, Ri divided by the initial value of the axis in two different cases. And you see that the model, ML means the model, of course, and num means the numerical results. You see that the evolution of the three different axes is not too badly reproduced. So the conclusion is that all evolutions are well reproduced including the softening due to mesoscopic localization. What is this? I'm talking about this final decrease. I will show you where it comes from. This is a picture taken from one of Vigo's papers. It's a different simulation, but nevertheless, it illustrates things very well. So you see, this was for a cylindrical void. So you see the initial cell shape, and because of the shear loading, you see that the strain concentrates within this thin region. This is in a periodic voidal material, so you must imagine that there is another void here, and so on. So you see that the strain essentially concentrates within a band, a planar band, the thickness of which is of the order of the void radius or void diameter. This is not microscopic localization because at the local scale there is no localization. You have found this material with strain hardening, so no local strain localization. This is not macroscopic localization at the scale of a cell. This is intermediary localization at some intermediary scale. I have to finish quickly. I now come to the butterfly experiments of Ductile and Moore, and you have a sketch of the experiment here. So you have this so-called butterfly specimen, which is loaded in tension here and here. And in the center you have a somewhat thinner region here, so this will concentrate the strain, and you will get a crack there. So the plate is subjected again to combined tension and shear. Model predictions are obtained by the finite element method, this time using abacus, with a full mesh of the specimen, which is provided by very kindly by Dirk Moore. And the elements are supposed to obey the extended Gurson model. There is a load angle which is connected to the ratio of the vertical and horizontal forces. Now the results. Here you have the vertical force versus the vertical displacement. Here the horizontal force versus the horizontal displacement for various values of beta, which characterizes the amount of tension as compared to the amount of shear. You see that the model reproduces the experiments rather well. The points where the experiments are stopped and where the calculations are stopped are not arbitrary. The experiments are stopped because there is an instability, so the specimen is broken, and the calculations are stopped because there is an instability. We'll come back to that. So you see here the experimental location of the crack and what you get numerically, which is again quite satisfactory. The conclusion is that all features are acceptably reproduced, including the final instability leading to failure. This is the magnification of the curves that you obtain. The calculations, we do not stop them arbitrarily, but because the calculations do not converge anymore, you see that the curve becomes completely vertical. So imposing a displacement, it becomes impossible to get some results. So the calculations diverge, and this precisely reproduces what happens in the experiments, because in the experiments you can observe an instability. So the conclusion is that this model has been, which extends Gurson's model to include void shape effects, has been implemented into two finite element programs using what we assume is an optimal algorithm. We have compared the model predictions with the first finite element simulations, micromechanical simulations of Tvergaard and co-workers, and also experiments of Ductile and Moore and butterfly specimens. And our conclusion is that this model seems to well reproduce the softening arising not from void growth, but from the change of shape and rotation of the voids. I didn't have time to comment on alternatives proposal which was made some years ago by Nash and Hutchinson. It's much simpler than this model. It's heuristic. It consists in modifying the evolution equation of the porosity. Well, it's heuristic, but it can be useful. I'm not criticizing this model. I'm just saying that this present model appears as a viable, more rigorous, but I must admit that it's much more complex alternative to Nash and Hutchinson's Hersey proposal to simulate ductile rupture and the conditions of low triaxiality. Thank you for your attention.